Hello, welcome to Econometrics Melody. In this video, we will see the relationship between partial correlation coefficient, beta coefficient, and t-score of the individual variable. So we have a partition regression y is equal to xp plus zc plus u, where x is the matrix of the independent variables, including the constant term, where z is the individual variable. And in case of partition regression, we know to calculate the beta estimate. And here we are focusing on the individual variable and its coefficient. So we can calculate the coefficient C, that is the estimate of C, making use of this formula. In order to calculate the coefficient C, we partial out the effect of X from Z, and we use this formula. And we have partitioned W into matrix X and individual variable Z. So this is the result of W transpose W. This is again a case of 2 into 2 partition matrix. And if we want to calculate the inverse of this portion, that is A22, then from the inverse of partition 2 into 2 partition matrix, we can calculate the inverse of this portion as well. We again actually partial out the effect of X, and we get this result. And here Z asterisk is that portion of Z when we partial out the effect of X from it. And let us assume that we know this relationship, the expected value of beta condition on X, this is equal to the true population beta, and the variance of beta condition on X, this is equal to sigma square X transpose X inverse. And here this is the case of homoscedasticity. We'll explore these topics in our future videos. And if the variance of the population residual, if it is unknown, then the distribution that we are going to get is the t distribution. We have explored this topic in our statistics series. So t is equal to estimated beta minus population beta, and for null hypothesis we assume the population beta to be 0, and as we don't know the population variance of the residual term, so we estimate making use of the sample variance, and this is equal to E transpose E divided by its degrees of freedom and X transpose X inverse. So applying this property, if we want to calculate the t-score related with this individual variable Z, then this is equal to its beta coefficient, that is equal to C, and under the null hypothesis we estimate that the population beta, this is equal to 0, divided by sigma square, and as we don't know the value of sigma square, we estimate it by the help of a sample. So U transpose U divided by, and matrix X, it has k columns, so if we add additional one variable, then it is k plus 1. So in total the degrees of freedom is n minus k minus 1. And X transpose X inverse, so in place of this X transpose X inverse, for this beta estimate C, we have the corresponding X is Z, so the Z transpose Z inverse after partitioning out the effect of X, and we get it as this value. In order to get rid of the square root, if we square both the sides, we get this result. And if we operate it, the degrees of freedom will go to the numerator, as well as the Z transpose asterisk Z asterisk inverse, this will also go to the numerator. And we'll make use of this relationship. Actually, we'll build on this relationship for today's topic. For this partition regression, we are focusing on this individual variable Z and its coefficient. And in order to partial out the effect of other independent variable X, we are creating the residual maker matrix. Now let us pre-multiply both the sides by this m, so this is my, and let us write my as, so we have partial out the effect of X from this y. This is equal to, what is the residual after running X on X? So this should be, there should be no residual, so this term is 0, plus from this Z we are going to partial out the effect of X again. So let us represent it as Z asterisk C plus M. As this either term and X, they are orthogonal, so if we run a regression of U on X, the residual should be equal to the dependent variable U itself, because X and U are orthogonal. And if we run a regression of U on X, then the error term, let me call it is theta, then the error term theta should be equal to U, because this B is equal to 0 because of X and U being orthogonal. Now we can estimate this C, this is equal to, from here we can also write this as, also we know that the partial correlation coefficient between y asterisk and z asterisk, that is after partialing out the effect of X, so this is, so let us square this. Is the correlation coefficient is free of the scale as well as the shift in the origin. This is equivalent to covariance of y and z, root under variance of y and variance of z. In both the numerator and denominator, we divide it by n. That is why they cancel out. Here root under n into root n. If you multiply it, this will be equal to n in the denominator as well, and in the numerator also it is n. So we cancel out, and we have written simply this term. So this is the square of the partial correlation coefficient between y and z, and to both the numerator and denominator, let us multiply it by, and this equation 1 can also be written as, because c, this is our scalar, so we can write it in this form as well. Because the numerator, this is of order 1 into 1, and the denominator is also of order 1 into 1, because both z and y, they are the vector of order n into 1, and z transpose is of order 1 into n, and y is of order n into 1. So if we operate it, this will result in a pure scalar. And if we substitute the value and arrange it, and as both y and z are the vectors, so z asterisk y, this will be equal to y asterisk z. So here this much, this is equal to c, and y asterisk z and z transpose z, so this is also equal to c. And if we further operate it, this is equal to, so we have already seen this relationship. We have calculated C making use of the beta estimate of partition regression, and we have established this relationship making use of partial correlation coefficient, and we have derived this relationship making use of the t-score of individual variable z. Now let us see t squared z, we divide it by n minus k minus 1, so this is equal to, so let us take the reciprocal of it, and let us add 1 to the both sides, and let us operate it, and let us take the reciprocal of it once again. Now to the right hand side, let us substitute the value of c by this value. Let me write it once again. So this is equal to, let us substitute the value of c, and we divide this entire term by, and let us cancel out the like terms, and if we further operate it, this will cancel out. So this is equal to, so we have manipulated this term, so this is again equal to, so from the relationship of partial correlation coefficient, we have seen that. Now in this relationship, once again, let us substitute the value of c square z asterisk transpose z asterisk by this value. So let us divide both the numerator and denominator by y asterisk transpose y asterisk. This and this will cancel out, and we need to divide this by y asterisk transpose y asterisk. So this, our result, this is equal to, so let me write it once again over here. So this is again equal to this relationship. This is also equal to the square of the partial correlation coefficient between the dependent variable and z, both dependent variable y and an individual variable z, after parceling out the effect of x. And this is also equal to the partial correlations between y and z after parceling out the effect of x. The first relationship, when we know the value of t, then we can calculate the partial correlation coefficient for that individual variable z. Similarly, when we know the beta coefficient for that individual variable z, and when we know u transpose u, that is the sum of the square of the either term, as well as the partial out effect of z transpose z, and accordingly we can calculate the value of partial correlation coefficient of the dependent variable and any one individual variable. So this is the relationship that we have derived today. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.